Welcome to the third lecture in the fourth week of our course Analysis of a Complex Kind. Today we'll start learning about Möbius transformations, which are special conformal mappings. This is a two-lecture part series, so we'll also learn about Möbius transformation in lecture 4. Let's start with the definition. A Möbius transformation is also sometimes called a fractional linear transformation, and it is simply a function of the form f of z equals az plus b over cz plus d, where these numbers a, b, c, and d are complex numbers such that a, d minus b, c is not equal to 0. So for example, you could say something like f of z equals 3z minus 4 divided by z plus 15i. In this case, AD, which is 3 times 15i, minus BC, which is 4, is not equal to 0, and so this is a Möbius transformation. In other words, you have a linear function at the top and a linear function at the bottom. What happens as you let z go toward infinity? Well, the term az becomes more and more important, and the term b becomes more and more unimportant, and the same thing happens in the denominator. So in the limit, f of z is something like az over cz, because the b and d have lost their importance given that az and cz are so big, and that is equal to a over c. Actually, you need c to be non-zero for this to be true. If c was equal to 0, then the denominator is just d, and az plus b over d goes to infinity, as c goes to infinity. So we say f of z goes to a over c as long as c is non-zero, and it goes to infinity if c is equal to 0. We therefore allow z to be equal to infinity, and define f of infinity to be a over c if c is non-zero, and f of infinity to be infinity if c is equal to 0. We can do a similar thing for the point that gets mapped to infinity, namely the point z for which you're going to be dividing by 0. When do you divide by 0 in this function? Well, when cz plus d is equal to 0. When is cz plus d equal to 0? Well, that is the case when cz is equal to minus d, or when z is equal to minus d over c. So we say that f of minus d over c is equal to infinity as long as c is non-zero. If c is equal to 0, then you can't make the denominator equal to 0. We therefore regard these Möbius transformations f not only as mappings from C, but as mappings defined on C hat, the extended complex plane, and mapping the extended complex plane C hat to the extended complex plane C hat. What's the derivative of a Möbius transformation? Well, we can just simply use the quotient rule. We square the denominator, which is cz plus d quantity squared. We write down the denominator again, cz plus d, multiply with the derivative of the numerator, which is a, minus the numerator times the derivative of the denominator, which is c. When you multiply through here in the top, you have a cza term plus dA minus azc minus bc. And you notice that cza and azc are the same thing. They cancel each other out. So all that's left is ad minus bc in the numerator and cz plus d squared in the denominator. Therefore, this condition, ad minus bc to be non-zero, that condition simply guarantees that the derivative is non-zero. Because if the derivative was 0, it would be to 0 everywhere and the function would be constant. So this condition, ad minus bc not equal to 0, guarantees that f is not a constant function. And automatically we know that f prime of z is then never equal to 0 for all z. Now notice if you multiply each of these parameters a, b, c, d by a constant k, you get the exact same mapping. You would get the mapping kaz plus kb over kcz plus kd, and you notice that you can factor out a k on top and bottom, and therefore the top then is az plus b, and the bottom is you can factor out a k times cz plus d. You can cancel these k's, and you're left again with az plus b over cz plus d. So you get the exact same function again. So by multiplying all these parameters a, b, c, d by a constant, you get the same mapping, and therefore for a given mapping, the constants a, b, c, d are not uniquely determined. You can multiply them all by a non-zero number and get the same mapping. A Möbius transformation is actually one-to-one and onto from C hat to C hat. If you wanted to prove this, you would do something like the following. Take a W in C hat and ask yourself, when is f of z equal to W? Well, f of z is equal to W when az plus b over cz plus d is equal to W. If you multiply both sides of that equation by the denominator cz plus d, that becomes az plus b needs to be W times cz plus d. If we solve that equation for z, we can find a z times a over here and a z times wc over here. If we bring that to the other side, we find z times a minus wc. Similarly, if we bring all the non-z terms to the other side, we have a wd minus b on the right-hand side. Dividing by a minus wc, we can solve for z and find that z needs to be wd minus b over minus wc plus a. In other words, no matter what w you pick, you can find exactly one z that gets mapped under f to w. That makes the function onto, but also one-to-one because it's exactly one z. There's not a second z. My formula gave me this is what z has to be. There's not another z that is also mapped onto w. That doesn't exist, and therefore the function is also one-to-one. So for each w, there is one and only one z such that f of z is equal to w, and you can include infinity in this discussion by just looking carefully enough and understanding carefully enough what the images and preimages of infinity are. Möbius transformations are therefore conformal mappings from C hat to C hat. In fact, Möbius transformations are the only conformal mappings from C hat to C hat. If you are asking for a conformal mapping that's defined on C hat and mapped to C hat, the only thing you will find are the Möbius transformations. Let's look at some examples. Suppose C is equal to 0, so this number is equal to 0, and D is equal to 1. The denominator is therefore just 1, and the function becomes f of z equals az plus b. These are also called affine transformations because they simply multiply z by the number a, which corresponds to a rotation dilation, and after that add b, which means add a translation. These mappings map infinity to infinity, and therefore also map c to c. No point in c is mapped to infinity, and therefore they map c to c. They're also therefore conformal mappings from c to c, in addition to being conformal mappings from c hat to c hat. And again, in fact, these are the only conformal mappings from c to c. In particular, if you in addition let b equal to 0, then the mapping is of the form f of z is equal to a times z. Therefore, you're multiplying z by a complex number, which corresponds to a rotation and dilation. If you write a as its absolute value times e to the I theta, you're rotating z by the angle theta, and you're stretching or shrinking it by a factor of absolute value of a. On the other hand, if a is equal to 1 and b is arbitrary, then f of z becomes z plus b, and that's simply a translation. You take a point z and move it to z plus b. Let's look at another example. Suppose a is 0, b is 1, c is 1, and d is 0. So the function becomes f of z is equal to 0 times z, az, plus b, which is 1, over 1 times z, that's my c, plus 0. But that is simply 1 divided by z. This is called an inversion. If you write z as r e to the I theta, what is 1 over z? What's 1 over r times 1 over e to the I theta? But 1 over e to the I theta, we proved, is the same as e to the minus I theta. So 1 over z is 1 over r times e to the minus I theta, which means f of z is obtained from z by taking the inverse of the length and taking the negative of the angle. In other words, if you're given the point z with a certain angle, theta, then you take the negative of that angle, and you take 1 over the length of z. So z was bigger than 1 in absolute value, then 1 over z is going to be smaller than 1, so maybe this is 1 over z. Now we notice, if z was of absolute value equal to 1, then f of z is still of absolute value equal to 1. So the circle, as a whole set of points, is preserved under f, even though points move around, but they stay on the circle. So f maps the circle to the circle. How about points that are outside of the circle? Points outside of the circle have a radius bigger than 1. After being mapped with f, they're going to have a radius less than 1, so they're going to be mapped into the circle. On the other hand, points inside the circle start having a radius less than 1. If you take 1 over that, they're going to be outside of the circle. So f interchanges the outside and inside of the unit circle while keeping the unit circle fixed as a set. Not point-wise, but as a whole set, the circle is mapped to the circle. Furthermore, a circle centered at 0, where is that mapped to? Let me again draw the circle of radius 1. And now let's draw an additional circle of radius, let's say 1/2. What is its image? Every point on that circle has radius 1/2. After mapping it with f, the images are going to have radius 1 over 1/2, which is 2. And so the image is going to be another circle, but of radius 2. And the same is true for any other circle. If you start with an even smaller circle, its image is going to have an even larger radius. But they're all going to be circles. So a circle centered at the origin is mapped under this one, mapping 1 over z, to another circle centered at the origin. How about other circles? Let's look at an example. What are the images of circles? Let's look at the circle the set of all z such that z minus 3 is equal to 1. So what is that? That is the circle that is centered at 3 and has radius 1. So this is k. The question is, what is the image of k under f? Let's say we have a point w that is in f of k. How did w get to be in f of k? Well, 1 over w needs to be in the original circle k. When is 1 over w in k? When 1 over w satisfies this condition. So 1 over w minus 3 must be of absolute value 1. Let's multiply both sides of this equation by absolute value of w. So we find that 1 minus 3w needs to be equal to w in absolute value, and then we can square both sides of the equation as well. So 1 minus 3w squared needs to be w squared. How do we find 1 minus 3w absolute value squared? Remember, the absolute value squared of a complex number can be found by taking that complex number and multiplying it with its conjugate. But what is the conjugate of 1 minus 3w? You can take the conjugate individually. It's the conjugate of 1. That's just 1 because 1 is a real number. The conjugate of 3 is 3, so all we have to do is the conjugate of w. And now we can multiply through. This is 1 minus 3 times the conjugate of w minus 3w minus plus 3 times 3 is 9, and w times its conjugate is the norm of w squared. That's this next line that I wrote out right here. So 1 minus 3w minus 3 times the conjugate of w plus 9w squared is equal to w squared. We'll bring this 1w squared over to the left-hand side and find that aw squared minus 3w minus 3 times the conjugate of w is equal to negative 1. We'll bring this 1 over to the other side instead. And now we divide both sides of the equation by 8. And what we end up with after dividing by 8 is the norm of w squared minus 3/8 times w minus 3/8 times the conjugate of w is equal to minus 1/8. And we notice that we can factor this. We can factor this left-hand side into w minus 3/8 times w conjugate minus 3/8. Because when we multiply this through, we get w times conjugate of w, which is this w squared right here. We get w times minus 3/8, which you have right here. We have minus 3/8 times the conjugate of w, and you get this one extra term. You get an extra term plus 9/64. That wasn't there before. So in order to make this a true equation, we need to also add 9/64 on the right-hand side of the equation. And that's what we did right here. So we see that w minus 3/8 times conjugate of w minus 3/8 needs to be equal to 9/64 minus 1/8. Now we see on the left-hand side, that is simply w minus 3/8 quantity squared. And on the right-hand side, we see 9/64 minus 8/64, which is 1/64, which is 1/8 squared. And then if you take a square root of both sides of the equation, you end up with w minus 3/8 is equal to 1/8. So what have we just seen? We have seen that w belongs to the image of the circle k when w minus 3/8 is equal to 1/8. Well, that's another circle. That is the circle centered at 3/8. So here's 1, there's 1/2. 3/8 is here, and the radius 1/8. So it's this little circle right there. So w belongs to the image of the original circle k, if and only if it's on this circle. In other words, the original circle k gets mapped to this little tiny circle. Here's the picture again. The circle k is right here, the circle of radius 1 centered at 3. Here's the unit circle in blue. Under f, it is mapped to this little tiny circle inside the unit circle. But it's a circle. So again, a circle was mapped to a circle. Let's check another example. Suppose we're looking at the circle z, such that z minus 1 absolute value is equal to 1. So it's the circle of radius 1 centered at 1. Here's the unit circle. And we're looking at the circle of radius 1 centered at 1. So here's the circle we're looking at. What is its, it's supposed to go to the origin. What is its image under f? Again, we do the same thing as before. W belongs to f of k. Well, how did it get there? 1 over w have to belong to k. When is 1 over w in the circle k? Well, when the distance between 1 over w and 1 is equal to 1. We multiply by w, square both sides of the equation, we get 1 minus w quantity squared is w squared. We do the same thing, we write 1 minus w quantity squared as 1 minus w times 1 minus w conjugate. We multiply through, we find that 1 minus w minus the conjugate of w plus the norm of w squared is equal to the norm of w squared. But now something funny happens. the w squared term goes away. They cancel each other out, and we're only left with w plus the conjugate of w, we brought this to the other side, is equal to 1. What is w plus the conjugate of w? That is 2 times the real part of w. If we divide that equation by 2, we find that the real part of w must be equal to 1/2. So w belongs to f of k if its real part is equal to 1/2. Which points have real part equal to 1/2? Any point on this vertical line through the point 1/2 has real part equal to 1/2. In other words, the orange circle gets mapped to that green line. Here's the picture. Here's the circle of radius 1, centered at 1, and actually unit circle as well. Its image under f is the vertical line through the point 1/2. Well, because f has the property that f of z is f of 1 over z is equal to z, we also find that f maps the line whose real part is 1/2 back to the circle of radius 1, centered at 1. And similarly, for the previous example, that little circle of radius 1/8, centered at 3/8, is mapped under f also to the circle of radius 1, centered at 3. So it appears that circles somehow can get mapped to circles or lines. Let's see what can happen to a line. Let L be the line through the origin given by the set of all z, such that z is of the form t plus it. In other words, is the set of all points where real and imaginary parts agree. What does that look like? Which points have the same real and imaginary parts? What's that line through the origin? If z is of the form t plus it, what's f of z? What's 1 over z? Another way of writing 1 over z is multiplying top and bottom by the conjugate of z, which turns the denominator into the norm of z squared and the numerator into conjugate of z. The conjugate of z is t minus it. And what is z squared? Well, z squared is t plus it norm squared, and you get the norm of a complex number by squaring its real part and its imaginary part and then taking the square root. But since you want the norm squared, it's simply real part squared plus imaginary part squared. That's 2t squared. So f of z is then t minus it over 2t squared. We can pull that apart into the real part and the imaginary part. The real part is therefore 1 over 2t. The imaginary part is minus 1 over 2t. If we call this number here s, then we see this is also s. So our number, f of z, is of the form s minus is. Where is s minus is? Those are complex numbers where the imaginary part is the opposite of the real part. These are these numbers of the form. So the orange line appears to be mapped onto the green line. Here's the image again. L seems to be mapped onto f of L. Now notice, this function f of z equals 1 over z maps 0 to infinity, and it maps infinity to 0. So if we include infinity in the line, then the line L gets mapped to the line f of L, which is the line through the origin, just at the opposite angle. So images of lines and circles seem to be lines and circles. And indeed, that is true. Every Möbius transformation maps circles and lines to circles or lines. So the statement is to be read as follows. The image of a circle is a circle or a line. The image of a line is a circle or a line. You could actually view a line simply as a circle through infinity, and you could then say Möbius transformations map circles to circles. We will see how to prove this in our next lecture. Let me finish up by showing you one more fact about Möbius transformations. Given 3 distinct points, z1, z2, and z3 in the extended complex plane, you can find a unique Möbius transformation that maps z1 to 0, z2 to 1, and z3 to infinity. So these 3 points determine the Möbius transformation uniquely, but you can also find one, and that's exactly what you wanted to do. You can actually prove this fact by simply writing out this Möbius transformation, and here it is. Let's check that this Möbius transformation actually does what I promised it would do. What is f of z1, for example? F of z1 is equal to z1 minus z1, well, that's 0, divided by z1 minus z3, that's not 0 because z1, z2, and z3 are supposed to be distinct from each other, times z2 minus z3 divided by z2 minus z1. Because this one term up here is equal to 0 and everything else is non-zero, that is equal to 0. So indeed, f maps z1 to 0, and it is a Möbius transformation. We have this extra factor here that makes it look a little bit different from a Möbius transformation, but it's of the form k times z minus z1 over z minus z3, and you could simply make that into kz minus kz1 divided by z minus z3, and now you recognize it is indeed a Möbius transformation. We just wrote it in a somehow different form. Let's next check what is f of z2. If I plug in z2, I have a z2 minus z1 right here, divided by z2 minus z3, and then I multiply by z2 minus z3 over z2 minus z1, and I see these terms cancel each other out. And this simplifies to 1. So z2 indeed is mapped to 1. Finally, what's the image of z3? z3 minus z1 is a non-zero number because z1 and z3 are not the same, but in the denominator we get z3 minus z3, which is 0. All the other numbers are non-zero, so this image is defined to be infinity. So indeed, z3 is mapped to infinity. Next up are constructions of more examples. How can you actually find Möbius transformations that you are interested in? This fact that we just proved in this particular Möbius transformation we just wrote down will be extremely helpful in creating your own Möbius transformations.